Ma'am,
Yes.
for the question 1 of assignment 2, so do we have to draw sigma donor, means MO interaction only for sigma donor and one for sigma donor pi acceptor and one sigma donor
Just a minute, just a minute.
pi donor
Slowly, slowly, slowly. For question number one,
one is ML6 sigma and pi interaction. So for that case,
MLC. See, I do not remember what I gave in the assignment, but what I expect you to learn how to write is that first ML6 with pi interaction, right? So it's a total interaction in presence of pi orbital. So in that case, you will find in the book whatever you want, pi or pi donor or pi acceptor, you can draw. And if you want, you just in a separate piece, you can write what happens to the d orbital when you have pi donor on, or you have pi acceptor. Or you can do it that the both the picture total ML6, one with pi acceptor and one with pi donor. Everything is available in the book, right? And these you'll understand.
yes, ma'am. Okay,
Okay.
okay, thank you, ma'am.
See, again, I am explaining it that you don't need to write. If someone wants to write it, just not looking at the book or interaction, but what I expect that the correlation diagram, whatever you write, must all the these lobes. I mean, these lobes. I mean that you have a positive and negative side, and they are must be matching with the other one, so that you put a different color. So I mean, you can one is filled and one is empty. That will also do. But to understand and each and every step, even if you draw it by looking at some book or anything, then just look at this. I mean, how does it overlap? How does this orbitals are orbitals are oriented? This is very important. And I am sure that if you do it by looking at the book, or if you just practice and then you write in the copy, just then you'll understand clearly that how does it happen. And just for that reason I have given it. Okay. So let us start today's class. So what happened last 2 days? I have given you some introduction about the spectroscopy and how does it happen. So what are the things that we have gathered, that there are free ion, there are microstates, and how does this microstates contribute. So today what we will try to do, we will try to check, try to see what happens when you have the D1, D2 system, and the electronic spectra uh, of this D1 and D2, D1 to D10 system. And then we will just check what are the things that we have learned in the last 2 days that we will incorporate and in a slow process, and we will end up at Tanabe-Sugano diagram definitely. But as I told you earlier also, and again I'm repeating the same thing, that Tanabe-Sugano diagram is a little bit difficult because it is considering all the my states, not states and then microstates and everything. So it is a little bit, a bit complicated thing. But if we go very systematically, very uh, uh, step by step, then you will understand this Tanabe-Sugano diagram just by looking at it. So this is our motto. So first the thing that these things you have learned. So I have just kept it in these class notes, because when you will read it, you can just have a look, and all these things you have already we have explained in the class. So now the what I told you, that when you have these states, all these things, then what are the things that govern the transition of electrons? So what governs the transition of electron is by selection rules. So what are the selections rule? So there are two main selection rule. One is the Laporte selection rule and another is the spin selection rule. So what does it say? So we will just be interested what about the selection rule. So what it says, that in Laporte selection rule, clearly it says that if you have, so this is the important part, the transition between the state with same parity are forbidden. So immediately what is the parity? The parity is G and U, right? This is the parity, you know. So did I keep? No, I didn't keep any page. So G and U. So the point is transition between states of same parity. So same parity. So what you have to remember? Same parity forbidden. Right? Same parity forbidden. So it means that G to G transition forbidden. But G to U is allowed. The second is the spin selection rule. Sorry, this will be like this 4A2. You can understand. 4A2, 2A2. Right. The next is the spin selection. So the spin selection rule, this del S is equal to 0 is allowed. So what does it mean? That transition between 4T, anything, I mean 4T, T1, 4, T2, any, I mean T1G, T2G. So if you look at this, then this 4 and 4 should match. And in case of spin selection rule, that del S is equal to 0 is allowed. So the transition between states of different multiplicities are forbidden. So what does it mean? That same multiplicity allowed. So it is also implied that, so they are telling in the forbidden term. So same parity forbidden and different spin multiplicities forbidden. So same spin multiplicities allowed. So del S equal to 0 is allowed. So this you just have to remember, right? The next is that the next point is very I mean practical thing. So what happens? So if you just look at the Laporte selection rule, then you see that in d orbital, T2G and EG, both of them are of G parity. So if both of them are G parity, then G to G transition are forbidden. So in that case, all DD transitions are forbidden. So if all DD transitions are forbidden, then the compound should not be colored at all. So what does it happen? So it means that when you have selection rules and if you have a compound in solution that is colored, then you have to understand that there must be something that is breaking that is happening, so that the forbidden transition are little bit allowed. Is it clear? Okay, let me give the explanation, then you will understand definitely. And in case of also this del S0, del S equal to 0 also, I mean both the selection rule. So now, but we have seen in almost all the cases that the complexes are colored, and in some cases the compound are extremely intense color. So from here one thing is a little bit understandable, right? If you remember that today is very important thing, so I am allowing. So if you think, so two things, so just it must strike in your mind that, so if you see a compound with a very intense color, in that case you can understand that it is not only DD transition, so something else is there. So I am just bringing the concept of MLCT. So generally, even all the DD transition are theoretically forbidden, but it becomes somewhat allowed due to the breaking of the selection rules by some means. So these are to the selection rule. Now we will learn that what are the things that sorry. Okay. So this is the term. Maybe I just keep it. Let me just. Okay, I have just forgot. Sorry, just a minute. Let me. Okay. So I just forgot. So what are the things? So let me draw a thing. So the first thing is that, so you have to, one thing is that what we draw is that exact L, right? Exact centrosymmetric molecule. So if for some reason this symmetry is not maintained, so what could be the reason? You know that I told you. So if all the L's are not same, and if the different orbitals are there, so the L's orbital interaction with particular metal atom, particular metal orbital is bit different. Right. So what we have told you, we have shown that this dx2y2 and dz2, both of them, all the things are or overlap similarly, but a little bit of differences are there. So what happens that if and also the chemical bonds undergo vibration. So these reasons, if for some reasons it this happens that the centrosymmetry, the symmetry of the molecule changes a little. So highly symmetrical octahedral is change a bit, or if you have a, let's say, ML5X or something, so you know that the symmetry changes, and in that case this selection rule is a little bit relaxed, and in that case you have uh, uh, the compounds, the transition become a little bit allowed, and also you can see the bright colors of these complexes. Now I shall come at the end, and if you have now the second case where the this Laporte orbiter, the Laporte selection rule also is relaxed. The first thing is that if you remember for this tetrahedral complex, then what we have shown, that tetrahedral complex we do not show any G or U term. So we generally don't give any such, it is not that symmetric, and we do not give any G or U term. And so the point is that, so the tetrahedral complexes are bright colored than octahedral one. Then octahedral one. Right. And also, in another way, you can just thought of this. I mean, when you have learned this valence bond theory, then you can remember that we have taken the orbital as sp3 or sd3 hybridization. And in that case also, in octahedral also, I mean, if we remember this hybridization of TBP geometry, that pz orbital, square pyramidal pz orbital, there is a little bit of, it is not purely d pz plus dz2 that hybridization occurs. So in that case, the purity of that p orbital or purity of a d orbital is broken, and also in that case it becomes a little bit allowed. So these are the two that takes care of this Laporte or this forbidden. I mean, it becomes a little bit allowed, and the strong rule that Laporte forbidden, the D to D or is not allowed, this follow. And then the second thing is that spin orbital coupling. So if you remember that when we go from 3D to 4D to 5D, so from lighter element, when we are going to the heavy transition metal, the spin orbit coupling, so the orbital angular momentum doesn't operate very independently, and the spin orbit coupling occurs. And once the spin orbit coupling occurs, then also the spin multiplicity actually is broken. Like if you take a triplet to triplet transition was not allowed, and when the spin orbit coupling occurs, then the spin orbit coupling, the purity of the spin actually changes. So in that case, the spin selection rule is relaxed, right? Now, one thing I don't think I kept it here. So one thing you must remember, that there are two rules. One is Laporte selection rule, and sorry. So it is already there. So one is Laporte selection rule, what is spin selection rule. So if the rule is, I mean, the observation is that if this is relaxed, this is more bright color, and this doesn't give, even if this is relaxed, the color is not that bright, right? So if you remember that D5 system, D5 of Mn2 plus, so Mn2 plus is a D5 system, right? So Mn2 plus is a D5 system, and in D5 system Whatever you take, the spin selection, spin remains the same, and then it is very pale color, very pale pink color, if you remember, very pale pink color. So now onwards, whenever you do any experiment, it is not that you have to remember. So one, if you come back and possibly, and then if you see any solution of a metal complex, copper, nickel, all these things, then you please look at the color and try, if it is very intense, try to understand the origin of the color, and it will be very interesting, right? Or you can anyway, you can also just see at it. So now we know that what are the states. Now we know what are the things that is happening. I mean, in case of this, what are the selections rules? We know that how we could relax the selection rules. So this is up to this. Now we will go to the D1 to D10 transition. Then we will come that what are the transition, and these transition we will put in the Tanabe-Sugana diagram. I do not know how much we can finish today, but we will not go very, I shall not go in a high speed. So let me know now that how is it clear or not. I mean, it is not very difficult, so it must be clear. So please let me know. Is it clear? Quickly. Don't waste. Okay. Now, some pages are there. So here I am just repeating it because if you remember, and one thing also, I actually I forgot to give this slides. I thought that I gave. So I shall in the when I shall upload it in the we learn in the this slides, then I shall also put the term for D2. I mean, I do not remember whether I kept it or not, so that it will be easier for you to understand. So let me take some. Okay. So now you see that these are the terms that correspond to this. So let us come to as D1 system. So what happens? Let us do. So D1 system. So D1 system, if I do, then this is one electron, and if it is one electron, it comes as 2D. Are you okay with this 2D ground state? It's okay, right? Because 2, 1, 0, minus 1, minus 2. So 2D is the ground state. So 2D, if it is, so D breaks into T2G Eg. So 2D breaks into, if I give it like this, sorry, if I give it energy and then with ligand strength, then it goes like this, 2D and then Eg and 2T2G. Right? So this is the D1 system. Now what happens to D4? Just look at it. So if you just look at this D4 now you just here, instead of keeping it empty, let us give one hole. This is the concept of hole. So here we are keeping a hole. So if you look from the side of hole, then this is a D1 system. Whole system is a D1 system. And if I just go at this electron system, then this is a D4 system, right? So D4 system, the multiplicity is 5, and you will find that plus 2, plus 1, 0, minus 1, minus 2. Then again, it is a 5D system. And the point is that it is a it is actually a I mean, the thing is that it is like EG, sorry, E2G goes up and EG comes here. So this is a 5D system. And now if I go for D6 system again, so DC system, if I just do it, then plus 2 plus 1, 0, minus 1, minus 2. So again, this is a 5D system, but here it is 5D like this. It is not whole. And if we go to the D9 system, then again it is consist of the opposite thing. So what is the uh, overall picture? The overall picture is this is for I am writing it, then I shall. Now the this is the 0 point and this goes like this. So it is increasing. I'm coming to the field, coming to the increasing field. Right. So this is coming as increasing ligand field. Then I need to put the D1 system, D2 system. So here it is D1, D9 octahedral. You can do it, no problem. And then D4 and D6 tetrahedral. So if you use the tetrahedral, then you will put T2, no 2G, no parity. And then here D1, D9 tetrahedra and D4, D6 octahedral. Clear? So is it clear? Now let me know. Is it clear or not? No response. Okay, now it is clear. So, what will be the transition? So, the transition is, so transition is T2G to, so transition is written in that way. Okay, so learn to write the transition. T2G to EG, EG. Now the point is that, so what do you expect? So you expect for all of them one absorption peak, right? One absorption peak. It is expected that you will have one absorption peak for that particular transition, but you will not see one transition. You may, I mean, if you just go to the Ti3 plus, then you will say that the band is like this. Okay, so that let me explain. I shall give the slide after us, but let me explain you and then you can understand. So as I told you earlier also, so if I take T2G1, so and then EG1, so what could be the point? It could be at dxy, it could be at dxz, and it could be at dyz, any of this orbital, right? And if it is EG1, so when it is EG1, it is going to T2G1 to EG1. Then it could be at DZ2 and it could be at DX2Y2. So you can say it in terms of Jahn-Taylor distortion. Generally, the name is like. So there are 2 points you must note, that when it is there, or it may be here, or it may be here, right? So there is also differences. So if we consider this, and if we consider here this one, and let's say here this one, it is not really. So if we consider that when the electron is in EG1, it could be here or it could be here, then what we are telling, that as these two orbitals are different, then the energy state is a little bit different, right? And we are telling that it is going from here, so either it can go here or it can go here. So instead of one single peak, we are getting the spectra like this one. Okay, I cannot draw properly. I'm very good at drawing. You can understand from the last classes, all the classes. But the point is that you can ask that then there are also these three things, these three orbitals are not also same. Actually, this is not same, but the energy difference between these three actually so small that it becomes a little bit broad, but it is not taken in, it is not properly show, reflected in the spectra. From the spectra, you cannot distinguish the difference. There are differences. If it is there, if it is there, and if it is there, there are definitely a little bit differences there, but it is not reflected. So this is the explanation. So I shall give the explanation, but I think you have understood this. Sorry. Next what we will do. So now here. So now we are done with the. So if I write D1, D2, D3, D4, D5, D6, D7, D7, D8, D9, D10. So if I write, so what are the things that we have taken care of? We have taken care of D2, D4, D6, D9, right? Now in the weak field, so if we are going to draw a thing named Orgel diagram. So generally Orgel diagram, the picture is for weak field generally. So if you take a weak field limit, then D5 ion is a high spin, and spherically symmetrical, and these three are similar. D0, D5 and D10 configurations are analogous, right? And this is with a S term. So there is no splitting. So if you remember, this is S term and there is no splitting and there is no DD transition as such, right? There is no DD transition. Only there is a little bit of difference between for this selection rules and for that the spin selection rules. So a little bit of very faint pale color we can see. So in that case, we are taking care of D5 and D10 and also D0 if I write here. So this is 6s. This the round term for the D5 ion is 6s. Now let us do something for D2. So D2 is a real thing that we should do it. So what is the, okay, it will be 12:43. I can go clearly. So now D2. You have learned a lot about D2 and I shall put the actual microstates that is for the D2 system um, ground state that I shall give. I mean, you can also do. So let us do that. What happens when a D2 system? So D2 system, we have seen that the 3F is the ground state, right? And then you have the 3P. If you remember from the last day, you have these things in your slides. So if this is the term, then 3F. So if I go here again, so what does breaks? 3F breaks into A2G, T2G and T1G. So 3F breaks into A2G, T2G and T1G. And as this is the spin multiplicity, I can keep it at. Now what does the P term goes? So P term goes to T1G. So 3P goes to T1G. T1G. Now generally we, for sake of understanding, we keep it as T1GP and T1GF. Now the point is that from the ground state term only, we know that 3T1GP term will be of higher energy than T1GF. And even if it is not in the Tanabe-Sugano, I am not drawing right now, but if you remember what I tell, that two similar states generally repel each other. And if now I give an energy diagram, then what happens? 3P, and if I give 3F, then 3P is T1GP. And this is 3T1GF. And this is, I'm coming to the explanation. 3A2G. It splits with 3T2G. Now, let us correlate with the original thing. So what happens? You have for D2, T2G2, EG0, it can go to T2G1, EG1, it can go to EG2. So this is the term that goes to that happens. I mean, if we go to the d orbital system, and then you have the T1, 3T1G is corresponding to any 2 electrons in any orbitals dxy, zx and dyz. Right. So it can be, and it is like, sorry, I cannot draw it like, sorry. It can be like this. It can be like the, sorry. It can be like this, or it can be like, so this is the 3T1G. It can be any of them. Then we have, I'm going to the next page. Space. Then we have T2G and T1GP. Sorry. T1GP. And we have 3T2G, 3T2G. So these are T2G1, EG1 system. The lower is the 3T2G, right? So 2 electrons, here you have to understand a little, 2 electrons lying mutually perpendicular dxy and dz2. Then repulsion is less. Okay. And upper T1G P 2 electrons are in, let's say, dxy, d2, x2, y2. So repulsion is high. So in that way you can, you can give it like, if it is dxz, okay, in that way only you can explain the difference between these two energy levels. So, and then Ta2G corresponds to these two, corresponds to these two, and Ta2G corresponds to T2G0, Eg2 system, and it is, only one in dz2 and one in dx2y2. So it is explained in that way. So now this is, then let me come here. So this is called the Orgel diagram. Orgel diagram. Let me explain it a bit. So if this is the D2 system, and if you go to the Orgel diagram, this is called Orgel diagram, and here this free ion, and generally they are with strong field, it is going to the strong field. So this is a miniature of this Tanabe-Sugano diagram, where we almost take all the things that is needed for our to understand the transition. And what we have, that if we do the calculation, we can see that this D27 system and D2 and D7, these two are like, I mean, this is for octahedral, so we can put it for the tetrahedral as well. And this D3 and D8, I shall from this picture, I may ask you to do the transition for the D3. I mean, the way I did it, you can draw, you can deduce it, and I shall ask next day that how do you think you have deduced it for the D3 system. But D3 system, again, a little bit what you have to find out the this ground term, and that then this ground term, what is the ground term? This ground term is A to G. Then you see that in that case the ground term is A to G, and how does it happen? So this is the Orgel diagram, and today I shall just finish it, that this is when you, what you are taking. So you have, I do not remember the what was the other order, like, but I remember there were one A's, there were on D, and all these things, terms for the D2, right? The last day when we have seen that there are terms for D2, I have shown you. So this Orgel diagram gives you a very simple explanation, whereas if you now just go for Tanabe-Sugano, then you just see that it takes care of all these terms, right? All the other terms is also, because there is the, as I told you, this is the free ion, then it is the octahedral symmetry level, and this is in the presence of ground field. And this part actually is when with the field, I mean with the B is not taken care of here with the B, because with the B it will change a little bit, that I shall explain clearly in the on the next class. That here, without taking the nephelauxetic effect, without taking the Raka parameter, I have not told you nephelauxetic effect, so I shall not tell you the term. Next day we shall explain it. So without the Raka parameter, without considering Raka parameter, this is the way it is written, and then with all the configuration, and then we have to look at this, that what transitions are allowed according to Laporte and the spin selection rule, what are the possible transition and what actually happens. And if you remember, this one is the real Tanabe-Sugano. So here, if you, so what is the difference? Only the a little bit of energy difference is there, which is taken care. This A, B, C parameter, Tanabe-Sugano diagram is reflected like this. So what we have, just the blue lines that right now we have taken care of. You see 3T1G, 3T2G, 3T1G. I mean, if you write it P, and if you write it F, and then this is 3T2G. So among these all possibilities, the we are interested because of for the transition that are within the UV visible and the visible range. We are only interested in this blue colored states, and the transition among themselves from the lower to the higher will give you the spectra. There may be a little bit, I mean, maybe, I mean, if there is expected is like this, then there may be some small broken things, that is for the symmetry thing and all these things that we will take care of. So there, today I end there. So I hope you have understood these things. And now within 5 minutes, if you have not understood anything, please let me know. But this part you have to understand very well, because almost all the questions from the spectra comes from here, and with with all definitely with some tricks that their expected is 3, you can see 2, their expected is 4, you can see 5, their expected is the sharp peak, you are taking a little bit curve is there, so and shoulder is there. So these are the things, but this organ diagram, if you understand clearly, then you can understand the Tanabe Sugano, because Tanabe Sugano, what I told you, you have to read. So only the possible transition you will look at, and as I kept it in the different color so that you can understand. And the parameters, I shall show you how to calculate the B value, and from there, as you can understand that we are thinking, I mean we are doing all these things like everything is there in the position, but what we will do, we will need to there will be a covalency, and that I shall come the term today, I shall not explain. So let me know if you have understood this or not, and I shall request you to again read it once more so that it will be easier for you to understand.